So, welcome to everybody. Thanks. So the seminar of today has the strange, Italy will be the first of a series of talk that we decided to put under the general title, Why Trust Science? Which might sound strange, but the idea is not mine, comes from a very nice book that I've read recently by Naomi Oreskes from Princeton. And she's trying to face the wave of current science denialism by even from a sociological and even epistemological way. So in the end, I mean, are we convinced that we should trust science? So can we ask ourselves, from scratch, what do we have to do? And then she gives the answer that she gives is yes, but then she, in order to reach this conclusion, restarting from scratch, she really makes an interesting point. That is that if we want to defend science, we have the old way that science was seen. So the individual heroic scientist who reproduces the results that are known in his lab, that we all know is false. I mean, who can reproduce the results of any of your paper except maybe one lab on the other side of the Atlantic or something like this? So this is not the reason why we should trust. The reasons that we are told in high school are not the real reasons we should trust science. And she makes an interesting point that I suggested to read. I have the book in my office. Whoever wants to take it, I've already read it, so you can come and have it. Is that we have to trust science because it's a collective effort. Because it's a collective effort from a lot of individuals across times, and the more these individuals are diverse, the more you trust science. Because as we know, population coding, if you have 1,000 persons, but they're all exactly the same, then there's no extra information. So the more science is a diverse and collective effort, the more we should trust it. And that's also the right way to communicate it to the people. And so this is just the general thing. In particular, even the book is called, is thought to be a very general book, but it's 80% about climate. And why is this? Because I think that right now, science denialism has different forms, but the most dangerous and urgent one is about climate change, climate crisis, if you want. And the reason is that about tobacco is causing cancer. Well, in this case, denialism came from funds from companies. And denialism about vaccines, this came largely from ignorance of individual people. Climate denialism is a perfect storm because it's both ignorance by people. And I think that the ignorance is our fault because we weren't able to tell the others what are the results. So we have to do more efforts to explain it. But then there's also corporate influence. This has been, there are reports everywhere, New York Times, so they're actively funding the climate denialism. So it's already Novax plus denying of tobacco cancer, plus right now it's even government-based. So there are different governments that really actively support climate denialism. So it's really a particularly strong form. And I think that as a collectivity of scientists, we have to do something. We have to stand it for the sake of science, even before that, for the sake of the planet. And in these dark and difficult times, for me, since I discovered it a long time ago, so I wasn't even working here, it was like 12 years ago, I discovered the reports of IPCC. So the reports of IPCC, Intergovernmental Panel on Climate Change, which are going to be the subject, are really, for me, a light in the darkness, because they're really a collective effort, taking into account, they are crystal clear with all the asterisks of the significance of the different tests. You can really, everybody of us is able to read it, okay? And I think we have also the duty, and this is something that, again, I'm trying to do for more than a decade now. I'm doing meetings in the schools in Florence, explaining to high schoolers these reports, okay? But this, I was doing it as a citizen who understands the science, okay? I'm not a climatologist, so in order to share the news and to, if you want, also hopefully to involve scientists in this, I said, okay, I'm not at the level. We have to upgrade it, and so that we want to go to the source. So we're lucky that two scientists that contributed in first person as lead authors to the sixth Intergovernmental Panel Climate Change report have accepted to come with us and to discuss with us the results that they have. And so I leave them the floor. I'm very happy to have you here, Annalisa Cherchi and Susanna Corti from CNR of Bologna, the Institute for Science of Atmosphere and Climate. And they're both experts in modeling. And what I liked is and understood after reading their books more precisely, is modeling not only the direction, but how good is the predictability of the direction in which you're going. Okay, so not only the first order, but the second. We are among scientists, so this is thing that I don't tell to the high schoolers, but not just the first order, but also the second order. So how good are our estimates about the future of weather and climate, that are two different things? So thanks again for coming and welcome.
Thank you. Thank you, Alberto, for the introduction, and thank you also for the invitation. So I'm Annalisa Cherchi, and I work at the Institute of the Atmospheric Sciences and Climate at the National Research Council in Bologna, and I'm a climatologist. And since I started to do science, I work with climate change, climate variability, and climate models. So today we are going to share the seminar. And I will start with some aspect of how do we know about climate change. So what are the instruments that we use, and what is the science that is at the base of our understanding of climate change? And then Susanna will go more in details on the outcomes of the last IPCC report that we contributed to as lead authors, and what is the IPCC and all the knowledge that is behind that. So starting with climate science. Oh, it's a bit. So starting from these slides, because in 2021, the Nobel Prize for Physics has been awarded to the science of climate, and the prize has been divided by Giorgio Parisi and Sicuro Manabe and Klaus Hasselmann. So it was given to Giorgio Parisi because of the discovery of the interplay of disorder and fluctuation in physical systems from atomic to planetary scale, and that is at the base of the understanding of the complex system. And as the climate system is a complex system, the other part of the prize was awarded to Manabe and Hasselmann, who are the pioneer of the modeling of Earth's climate. So, and the prize was for the physical modeling of Earth's climate, quantifying variability and reliably predicting global warming. So this is the base of the climate modeling. And this has been a very important step, at least for me, because I was studying physics, but the physics of climate was the small sister of the science of the physics, because physics was the theoretical physics and atomic physics, but not this part. And this is instead a very still part of the physics. So the climate system. This is così. The climate system. So the climate system is the interaction between the realms that are part of climate, so the atmosphere, the ocean, the land surface, but also the biosphere. And those the interaction and the changes that occur between this, so how the water changes from solid to liquid and vapor, but also all the exchanges between the different realms, so the changes of momentum, the changes of radiation, the changes of energy. So all these exchange build the climate system. So that is the interaction and all the feedbacks that are part of the climate system. So it's a very complex world. There are also external forces that work and influence how climate changes. And they are of two kinds. So they are of natural origin, like the solar changes, the solar radiation, and also the volcanoes, because they can put into the atmosphere a huge quantity of gases that have interaction in terms of radiation, but also as particulates that are in the atmosphere, and then can have effect into the climate, but they are of natural origin. But there are also forces that are of anthropogenic origin, because they are part of the emission that we have because of our life. So the industry, so all the emission of what are called the greenhouse gases, but also how we deal with the land surface, so the land use, the agriculture, building cities, all these changes that we include in the system have an effect, can have an effect into the climate. So how do we study climate? So the first thing is using observation. So we have observation, so we have measurements, for example, in the atmosphere in terms of temperature and precipitation, and also in the ocean, temperature, salinity, and current. So, and that starts when you have instruments that can permit you to do measurements. But we can go very back in the past because we have proxies. So we have indirect measurements of information coming from other sources like ice cores or pollens, or there are different sources of information that can give you indication of how was the climate at that time, so what was the temperature, and then you can have information. All the measurements are taken in one point, so then to have a more large scale information, you need networks of measurements, and a big input has been up to the end of the 70s when the satellites were started to be used, and they started to give a global coverage of information and of observation. So considering this, so considering the information that come either from the networks of observation, but also then from the satellites, what do we know about the past changes? So if you look on the left, you see the surface temperature in terms of trend, so in changes of a degree per decade, and you see the trend measured from 1900 to 1980, and you see that there is like pink and orange colors that includes that there has been a warming. But if you look at the panel in the bottom, that is the trend measured in a like shorter time, that is 1980 to 2020, you see that the colors become more and more reddish, and that is an indication of how fast, how more the climate has warmed, and also give an indication of how fast it has warmed, because in a 30 years time, the increase has been much larger than in the other time. There are regions where you see a lot of process, and there are regions where there is no statistical significance. So the information that are taken in that points are not statistically significant because there are not enough information in terms of data. That okay, so I was saying that we have this primitive equation system. This is for the atmosphere, but it works also for the other realms. And if we think of what are the tools and the aspect that we need to think in terms of what are the ingredients for having a general calculation model, in this case for the atmosphere, that at the end it is a three-dimensional representation of the primitive equation system to reproduce the dynamical and physical mechanism that works in the atmosphere. So there is a set of equations that I have shown you before, so for the motion, but also for the energy and the other conservation. Then we need a representation of all the variables that we need in the horizontal and in the vertical. We need numerical techniques that are used to solve the equation, that are nonlinear equations, so we don't have one solution, so we need integration space and time. And then we have the physical representation for all the processes that we need to deal with within our system. And then we have boundary and initial condition, whose importance changes according to what kind of experiment and what kind of simulation we are doing. And that in terms of history on how the models have developed in time, this is a sort of time scale and changing in time of how the different realm has been developed and then coupled together. So the model started with the atmospheric model alone, that then were coupled with land surface schemes at the beginning. Now they are full model components even for the land surface. Then the evolution of ocean models started in parallel and then were coupled, and also for the other aspects. So each different kind of processes and representation was then developed offline and then happening, trying to arrive at a situation where we have very complex and full coupled Earth system model. And then if we go in terms of how this is represented, so we have on the left a scheme of how the surface is organized into cells, where in each cells we have all the equations that have to be solved and all the processes that have to be taken into account. So the distribution of precipitation, the distribution of the radiation. So in each cell, every equation is solved and integrated in time and space with the neighbors. In the upper, there is all the information that relates with the part of the climate that is related with the physics, but then, as I have shown you before, recently, also the aspect of the biochemistry, so the carbon cycle, the other chemical properties of the atmosphere were started to be coupled, the roles of the biochemistry in terms of what is in the surface, in the vegetation, but also all the biochemistry that is in the ocean. And this is a scheme where you see the exchanges that occurs between the different components of the climate model. So the exchanges for the vapor, information on winds, temperature, and then salinity and currents, and there are continuous exchanges between them. What happens in terms of how the information are integrated and are discretized within the surface, there is a dimension of the basic green that is the minimum scale of the phenomena that can be resolved. So there is a time and spatial scale that is the minimum that has been resolved, and this can increase and changes according to what is the computational power that you have on hand that you can use. But there are still, even thinking of the evolution that we have, when I started to do this job, I was using models, was the dimension of a grid was 300 kilometers for global models. So now the state-of-the-art global model are around 100 kilometers, but they can arrive at 25 kilometers for some application. But still there are computational restrictions that are needed that we have, because we cannot, it's not always that we have all the information to do all the computation. And the other point is that all what is below that scale, that is 25 or 300, all the subscale phenomena and the cumulus convection, the front, the turbulence, they are all processes that are below, even at the finer global horizontal grid that we can have at the global scale, cannot be resolved explicitly, so they have to be expressed in terms of macro scale parameters. So that's why we have parameterization that help us to have this kind of processes. This is to give an idea of the scale, the horizontal scale, and the time scale of the different processes that occurs in the atmosphere, and that can be represented in the model. And of course, if you are thinking that you are around this kind of dimension, there are a lot of processes that are not considered or that have to be parameterized. And this is to give an idea of the evolution of the horizontal resolution for climate studies. So starting for the first assessment report that was published in 1990, and the models that were, and the experiments that were done at that time, were around the 500 kilometer resolution, then 250, and then in the last report, we are around 50 and 100 kilometer of the resolution for the global model. But you can see how the resolution can change the details of the surface if you go, for example, from 130 kilometer to 25 kilometers. That is, today is the scale at global resolution below which is very difficult to go thinking of doing climate simulation. And this is sort of future or something that is going to start it. So this destination Earth, where they are trying to work doing replica of the planet going at very, very, very high resolution. So there is a lot of effort that is going to be done there, a lot of studies that are done, but this is still a bit far from thinking of doing climate in terms of long climate simulation that can be done at this very, very high resolution. But this is the future. That is what we would like to reach. Okay, but what is the point? You will see probably the figure also from Susanna's presentation, because it's taken from the last IPCC report. But what is the point here? the point, if you look at this figure, is that if we think of the global surface temperature anomalies, and we look at the black line, is the anomalies as has been observed, is taken from the observation, and they are anomalies with respect to a reference period. You see here at the beginning of the time that the oscillation are around 0. So this is the reference period with respect to the anomalies are taken, and this is the observation. Then we have two colored curves. One is with simulated and human and natural forcing. So this is done with climate models, state-of-the-art climate models. This is taken from the CNR-ISAC framework, that is the last international framework where this kind of simulation has been done from different institutes around the world. So doing the same kind of experiment with the same kind of forcing, and then all the simulation together. And you can see that in this case, the orange curve follows the changes and the trend of the black curve. And here is the same model used, but forcing with different kind of atmospheric forcing. So considering only the changes in solar and volcanic, the solar forcing and the volcanic forcing. The difference between the two is that the orange follows the trend, while this cyan one does not. This is how the climate will change without any anthropogenic effect, and this is how the climate change with the anthropogenic effect. And this tells us that the global warming that we are experiencing in the last decade is because of the human influence. And it's telling us also that this changes has no precedent in the last 2000 years. So we use models to do this and to understand these changes. The other point the other aspect that we do with models is, so if we can trust the models in what they do in historical simulation, and the simulations are realistic, then we can trust them for future simulation. And that is what climate are really looking forward to. So to give information about how the climate is going to change. And to do that, we refer to these climate scenarios. The climate scenarios is an evolution in time of potential emission in the future. And these scenarios are built using economic models. So thinking of how the society is going to change, how the industry are going to change. So what are the different possible evolution in the future of this social and economic aspect? This will end up in amount of emissions. So according to how the society will evolve, how many people, how many industries, of kind of industry, etc., the emission of carbon dioxide, methane, and all the greenhouse gases is going to change. So the scenario are these changes in the emissions that end up in this kind of curves. These are the scenarios that have been considered in the experiments that have been used in the assessment of the last IPCC report. And you can see that according to how this, depending on the kind of society that we have, the emission can change. So we have scenarios where the carbon dioxide continue to increase, and other where there will be possibility that there are a decrease in time. And then the models do the projection. So the models take these scenarios, so this evolution in time of the emission, and say if the emission follows this line, follows this change in time, then the climate will be. And the climate will be is the projection. Then Susanna will show more about this, but this is just to give an example of what, for example, for the global annual mean temperature. So you see in black what has been the simulation for the past, and then you see the possible changes of the temperature following the climate scenarios. And then there is also for the Arctic sea ice and for the acidification of the ocean. Of course, you see that one other thing that you see that there are shades. So whenever I have shown models, there is shades around the lines, and that's because there are different models and different representation, and there are uncertainties associated to the changes. The fact that we have uncertainties doesn't mean that we cannot trust them, but it means that we know that there are uncertainties, and we are able to know what kind of uncertainties, and we are able to say, okay, this is going to be the information, this is going to be what is supposed to happen with this kind of uncertainty. And the measure of uncertainty is the base of the physics. In any case, any measure that you do as an uncertainty, if you do a measure of this table, you have an uncertainty. So, but that doesn't mean that you are not able to measure a table, and that's the same for the climate. And for climate projection, the uncertainties can be organized into 3 different kinds. So one is associated with the internal variability, and that is associated with how the climate changes independently of all the forcings that are applied. So it's the internal what we call internal variability. There is an uncertainty associated to the models, that is the blue one, and this because models have these parameterizations that I've shown, so we cannot, and the equation are not one solution, and etc. And there is also an uncertainty associated with the scenario. One difference between these 2 plots that I have included here is considering the projection in the short term, so in 2021, 2040, or toward the end of the scenario. And you see that there is a change on the importance. This is the percentage, the weight of that kind of uncertainty. And this is for the precipitation. And you see that there are differences. So this green line becomes more important if you go very far in the future. At the same time, this orange that is associated with internal variability becomes negligible if you go very far in the future. So the more you are close.
Sorry, what's on the y-axis?
The y-axis is the latitude. So this is measured in, I don't remember, here is land and ocean and land, so over the globe, but at different latitudes, because there are differences also in terms of how do we know the information, because some regions of the world are easier to be considered and to be reproduced than others. And then there is the uncertainties in the models that more or less maintain the same kind of importance, but that because it's intrinsic in how the models represent the processes. Last thing that I want to show you is just about the complex. So also this is taken from the changes in the circulation of the atmosphere and how they are associated with the changes in the water cycle. But it's just to give an idea of the complexity and of the needs that we have in terms of all the information that we can retrieve for the model. So it's not just about how the temperature is going to change, but also changes that relates to how the winds is changing. So how the circulation and all the kind of regions where this is the IPCC, so the region where we have the maximum concentration of precipitation in the tropics. So all these changes in the importance also of having the possibility to study it with the models, that because in the models all this information are together, and so we can follow one with the other, and we can have information and understanding of how they are changing together. With the observation, you have always one piece of information with respect to this global scale picture. Okay, I have concluded. So just to show that the climate science is relatively new in the sense of how it has developed, and we have started to use massively global model, but it's grounded on solid knowledge of the physics, that the climate models and also the observations that we have are the tools that we have to understand and study the climate, but they are continuous developing. Models are continuing developing because the resolution increase, because we have more information, because we need also the observation to have a better equation for our models, because the more we know from the reality, the more we can have a better simulation of the reality. And in all this, we are aware that these tools have limitations and uncertainties, but they are the best instrument that we have now to understand and being able to know about how climate has changed and how it's going to change in the future. Thank you.
Questions now or
yes? You want?
There are any questions?
Thanks a lot for your talk. I'm an economist here at the school, and I work with climate. What we do is to, as you pointed out, understand impacts and try to give you the other part of the picture. So projections about how things on the economic side might change in the future. And my overall impression is that climatologists have done a much better job than economists that try to project these things. But having said that, during the last period, I've been working on the impacts of precipitations. And what I've noticed, you showed a little bit of this in the Sydney bundles of models, that there is a huge model uncertainty in precipitation, which I didn't expect because we are used to work with temperatures, and temperatures, all models, they agree very much among each other. While in precipitation, especially in certain areas, in the Sahel region, in the sub-Saharan area, they conflict a lot. In one research, we find that probably the most worrying impacts climate change on the precipitation side are exactly going to be that region in the world. So I was wondering, in your opinion, what will it take from a point of view of a climatologist to fill these gaps? And what's the main problem? Because you showed a graph where you had a lot of axes in the precipitation. Is it a problem of missing observation? Is it a problem of something that you still need to understand from the modeling point of view?
Okay, the point for the precipitation in terms of models is not something that we don't have full knowledge about, but is most related with the resolution. So the problem of precipitation is that the processes, of course, have a scale, a spatial scale that is much smaller than the scale that we use in the representation in our model. So the parameterization there have huge problems. So that is one point. There is also a point associated with what do we know about how precipitation has changed, because we have less precipitation, but this is less crucial with respect to the problem that we have in the representation of the processes. The point is, so there are a lot of studies that are going toward very, very high resolution. So trying to arrive at the convection permitting model, so arriving at the resolution of the models where you can resolve the convection effectively. The point is that at the moment, with that models, we are not able to do this kind of study. So we are not able to cover the last century and then to cover one century of the futures, because we don't have the computational power to do that. Still, it's not necessary that if you arrive at the scale that you need, you have solved all the problem, because there is also the interaction with all the other parts. So precipitation is not only because of rainfall that, how this precipitation changes is also associated with what happens over the land surface. So all the feedbacks that we have in the hydrologic cycle. So it's not just one point. So it's not that if you arrive at convection permitting, you have solved all your problems, because there is a lot.
Regional and global scale.
There is also problem of regional and global. Yes, so it is very complex. So we are going to work forward and going to have higher resolution, but we need also to go and thinking of how we can have better parameterization. So on this problem, but precipitation, yes, is a huge problem, but it's also what during the IPCC I was in the chapter of the water cycle changes. So the request was what we are going to expect over land. So what is going to change over land? What is going to happen to the precipitation? What is going to happen to the groundwater? And that, but that is the part that we are more uncertainties because of all this.
Thanks.
I want to think that I don't know if I understand this about the population and the demographic data. Is this a variable that you use, or based? I've seen some prediction about how this the demography and the population is growing. I think what things like.
Okay, this is
climate change.
Is an independent variable that you're using for prediction, or is it dependent variable like you mentioned?
Because you can see, I think, both sides.
But that is in the economic models. That is.
If you can come back to the future
But it
scenario.
goes in the scenarios, but the scenarios are not done with climate models. The scenarios are done with economic models. Okay, so the economic model has input all possible changes in terms of population, education, urbanization,
These are
GDP.
independent variables that they put
In the economic model.
in the economic model.
So
Okay.
then the output of the economic model is the distribution in time of the greenhouse gases, in this case, the carbon dioxide. And these are included in the climate models that produce the projection. In climate models, there is now the idea of having how the population is changing, so how humans are changing and directly influencing climate within the climate model, within the system model, but it is the final at the beginning of
I
the.
think it's also the reverse, because climate changes probably will affect how
Yes.
the population will grow.
Yes.
Where?
But this is not inside the climate model yet. Okay, so this is just information in the economic model to produce the scenarios. In the climate models, the humans are not there, are just there in terms of how they emit, but there is no interaction because even the migration are going to change because of climate. But this is not something that is coupled in the climate model, not yet. I mean, there are groups that are starting to do and to develop this kind of part of the climate, but not yet. It's not yet inside, and I don't think it will be in the next. Even in the next assessment record, so it's not something that will be included, I guess.
So, okay, one question that I wanted to ask was this one. So, and then one question and maybe a comment. So the question is, but the uncertainty about precipitation, even right now, you have to fight against them always. Also think about the politics of this. I mean, you fight with these people that are saying, so wasn't it about to be a drought? What about with the heavy rains? And the way I visualize them, but it's tough to explain. The idea is that because of the different way in which water is absorbed in the atmosphere, I'm talking about the non-specialists, but is then what I visualize it as the oscillation. There's more energy in the systems, so oscillations are becoming broader. So you have more heavy precipitation, and at the same time you have more drought. So. So that is this oscillatory aspect has to do something with the difficulty of predicting precipitations.
No, I mean the point that in a future with global warming, there is at the same time the possibility to have more extremes in drought and more extreme in heavy precipitation is associated with the physics and the thermodynamics. So it's just how the water vapors changes, so how the energetics works, but it's not necessarily something that goes with the oscillator.
Yeah, it's non-periodic, no per se.
Okay.
So
it's just, but at the same time, so how the energetics and the water vapor and all this stuff are works in the atmosphere can provide at the same time either more extreme in drought, but also more extreme in terms of heavy precipitation events that can be shorter in time but larger in intensity, and so they can coexist at the same time. They are not excluding one each other, and that is how I mean, because of the thermodynamics of the atmosphere, basically.
Then one comment for the student to try to join the two things. Okay, so I'm really when we model the brain. A lot of people here do model of the brain, and the brain is a complex system with multiple time scales. But usually we can neglect a lot of time scales because we know that the system is stable. So there's noise at, for example, there's noise at every level, but you know that in the end you're going to grab an object. Okay, I don't want to read 3 times. But usually you grab an object. Okay, because the system is stable. So you can neglect. We personally in my group we almost never model the molecular size, which would be the meter size. But then it came to my mind that maybe a comparison. So what happens, because at the same time you have that the baseline is shifting. That's what they're saying. So you have to model something, but the baseline is shifting. So you cannot neglect any time scale. So it reminded me, this is what we have to do when we don't study the healthy nervous system. So when we study a pathology, so we don't a pathology that is evolving, so we have there's not a baseline anymore. So we need to go back and model even the molecules that are going away and so on. So I was thinking, so why sometimes we are lucky and we neglect more scales than usual. We show that 7 orders of magnitude, 10 orders of magnitude Usually we don't. We model it from micro.
Yes, but all the scale that is below the grid is just parameterized, so we cannot solve all the time scale, all the space scale that we would need.
Okay.
For this kind of climate simulation, because we need also integration in time that will require too many computational power that we don't have on hand to do simulation in a realistic time, because I mean, you can wait years, but it doesn't make sense to wait years to have simulation 100 years. Okay, so that's why.
But please say something about what we say. It's not only because the system is in transit that we need all the time scales. Actually, it's because the climate spectrum is continuous, and we don't have actually a really cut for difference in frequency, so we can neglect. We don't never know when we can neglect. This is the main problem of also for weather predictions, basically related to the climate predictions. However, there are some cases in which we don't need all the scales. In other cases, which one little thing matter. And the problem is that we don't know a priori why this is the case. And well, now there are studies, and maybe with the help of artificial intelligence, I think more data, we can start better this problem. But this is actually the main problem of the complexity of this kind of science. I don't know, I know nothing about the brain, so it's, but probably it's there is more.
So we have a lot of separation. There are people studying molecules and the people
we don't have a real separation of scales in both in space and time. This is one of the main problems. And of course, Annalisa said that a given point one has to choose. Maybe there are other questions for Annalisa.
I have a question. So what can you, so we basically produce technology. So we started technology. So is there anything that we could do? I mean, in terms of, I don't know, providing new sensors that can be distributed over land or oceans, or I don't know, new computational tools and machine learning tools that can support your modeling effort.
Yes, from the observation point of view, all the technologies that develop sensors and all that can provide instruments that are able to have also different measures that we don't have. So thinking of properties of the soil that we know partially, some information and others that are needed. So, but then there is the need to have a coverage that goes beyond just one instrument placed in one place. But any developing technology toward this is, of course, useful, and there are campaigns that are starting to be considered and to be built. And also the artificial intelligence is the new frontier of how we can use to help us in doing some work. So, for example, speeding up some part of the simulation that can help to decrease the time needed for do something, and then leaving the other aspect later. There is a risk that there are a lot of people now that are trying to use artificial intelligence also to do prediction instead of the models, and there is always the risk to lose all what is. So the artificial intelligence is for sure an help, but we need to be careful in not doing too much and going to change what is the physical knowledge that is needed and that the artificial intelligence cannot have. So we need to be careful in crossing this. But artificial intelligence is now something that, I mean, we are having very inputs and very help from this kind of technology, because they can speed up some aspect of the analysis or and also part of the models. Susanna before was saying about how the spin up, that is the part of the models that needs to be done to arrive at an equilibrium, because the atmosphere and the ocean have a different time scale. So the equilibrium that they can reach has a different time scale. The atmosphere adjusts in very in few days, weeks, but the ocean needs years. And then all the simulation that is needed because they arrive at an equilibrium can be very, very long. And there is now some trying to use the artificial intelligence to speed up these processes and having, so for sure there is interaction and in these two aspects.
Thank you very much. Okay, so thanks.
So thank you for inviting me, Annalisa. And my talk will be a bit more general about the results of the IPCC. Probably most of what I'm going to show you know already, so it will be a bit of kind of relaxation with respect to Annalisa's talk, but then we can discuss also other things later on. So basically, just to come back to what actually was said at the beginning, that the IPCC was a really a huge collaborative effort. And we can see the numbers here, because this is the last IPCC, the number 6 IPCC started in 1988, and WG1 is the working group of the report that is actually focused on science, on the physics of climate. So try to understand, let's say, climate. At the beginning, there were a few words. So what we understand of climate, is climate actually changing? And the last question was, there is an anthropogenic influence on climate. These were the 3 main questions that were asked to the scientific community in 1988. And then there was this series of efforts. And in this case, you know, there are 2,034 authors, and good 30% new to the IPCC. Both Annalisa and I were new, so for us it was the first time to be leading authors in an IPCC report. And what is important is that actually we received 80,000 review comments, and we had to answer to each one of these review comments. And they were very important because there were 4 orders of draft. Number 0 and the review were only from a restricted part of the scientific community. And then from number 1, for draft number 1, this was open, the review process to basically everybody. Of course, there were comments coming from the scientific community actually directly involved in studies on climate change and climate weather and blah, blah, blah. But there were also scientists that were not involved. And then we had to answer to everyone. And all their answers and comments were checked. So I would say that seldom we see a peer review so strict, so complete, so strong. And it required a lot of effort to actually, but it was very useful because actually looking at the different draft, the report changed a lot and it became richer in information. And this is something that is never underlined, but is very important because it was really, and also for us was a really incredible experience. Kind of, we don't know if we would do it again another time, because actually we spent 4 years actually, and Annalisa more than me, because she was involved in many working groups and like that. But it was really interesting and good to be part of it. I wanted just to, before the IPCC, I wanted just to say something about, because sometimes, of course, not in this community, because you are all physicists and or not physicists, but let's say in the field, but actually it seems that we are doing something new and with magic instruments. So basically the science the science on which the study of the atmosphere, of the ocean, of the Earth system is a very old science. It's a classical science. And this is basically fluid dynamics, thermodynamics, and chemistry that it's known since 1 century and more. And one can see here that actually, you can see that the first that talked about the greenhouse effect was Fourier in 1982. And then there were all this progress, and it's interesting for the girls here that the first one that showed that the CO2 was warming the atmosphere was this lady, Miss Foote. She was recognized only because she presented the work that was an experimental work at a conference in the United States in 1856. But this, since women were not admitted, actually, she could. There were the proceedings. But I think that the results were showed by Erasmus. And only recently actually was recognized that she showed this. There is a paper on a British review, I think 2009 or so. So before that, nobody knew. And she was the first one. But then there was this famous work by the British scientist Tyndall and so on and so. And we proceed. But you know, up to the war in the 50s, actually there was this big problem, the big problem that we know the equations, we know the science, but what we do, not much, because basically the Navier-Stokes equation cannot be solved. It's still a problem, and if someone is able to solve the Navier-Stokes equation, can take the medal for ESA. Exactly. So it was a problem that was not tackled because of that. And the revolution arrived with the computers, the big computers. So basically, after the war, the 50s, the 60s, and the 70s. In the 70s, actually started just the first model, the first digital model of the atmosphere, and the solution of this model. And that was a really important date, 1979. In 1979, actually, there was still this problem with the nuclear winter. We are going to the ice age and so on. Of course, nobody here can remember, but not even I, but we know about that. And Cherchi was a physicist at MIT and very, very famous, and he died prematurely a few years later, but was the first one that actually showed that one commission in the US, that there was a problem with the CO2, with increasing CO2 in atmosphere. In the meanwhile, from the 1960, something, they started to measure the CO2 in the famous observatory in Mauna Loa in the Hawaii. So there were important times, and actually there was this problem coming up. This is why in 1998, the United Nations, the Commission, whether WMO, the Organization for World Meteorological Organization, something like that, decided actually to put this commission and so and so. So this is, sorry, I took a bit long, but it's important because basically the basis of all we are talking about are really, really well consolidated science. And this is very important. This is physics, it's not magic, it's not that black box model, and we know what is in the model. And the model there are the equations that Annalisa showed with, of course, parameterization and so and so, and way of solving equations that are complicated. But the kernel of everything is there. So this is what everybody knew already, but the last IPCC had to state it strongly again, recent changes in the climate are widespread, rapid, and intensifying, and unprecedented. And this was something that had been already stated since the third report of the IPCC that happened in 2001, so 20 years ago. But every time there is the need and to state it again strongly and strongly. And this is actually the, you showed this one before. No, well, basically this is the reconstruction of, of the temperature of the mean temperature of the planet. And these are anomalies, so deviation from a mean in between 1850 and 2020. What is really striking is that, of course, what is reconstructed with paleoclimate proxies and so on, so has a huge, very huge. Can you see if I do that? Yeah, yeah. So basically, you can see that the range of uncertainty is very large, and you can see also that actually in the past the temperature seems higher than in the reference period. But what is really striking, and something that should be noted by people that say that climate change, there are always climate change, is the rate of change. So basically what has been changed in this microscopic period, only basically only 150 years with respect to 2000 years in the past. And this period is basically magnified here. And you can see, and this is what Annalisa showed before, this basically this climbing and of the temperatures that is unprecedented. And well, so what happened in this 150 in 50 years? And this is the observed warming, about 1 degree, you know, and these are the forcing. We know that there's these greenhouse gases, and these are the forcing, and the total human influence has been estimated like that. So basically, these are all aggregated contribution of all the greenhouse gases. So not only the CO2, but the methane and the chlorofluorocarbons and carbons and other gases. But some of them actually they have a cooling effect. So this is the cooling effect of some of them, in particular those that act more like aerosols, the fact of the aerosol. So this is the effect. So we know, basically, we know what happened, we know what has been modified, and we know the mechanism in between. So basically, you have all the elements to say this is, but is not enough. And there was the counterfactual evidence. The counterfactual evidence is this that Annalisa has already explained. And this was very important. And a plot like that. Now in TikTok, there are many models, like around 60 for each of the bands. But the first time that was shown something like that was 20 years ago, 2001, third IPCC report was the first time that was a model counterfactual evidence that without the component, without the human component, human influence, that the temperature would have been different. And this is also what the model can do in terms of how they basically, this is a general indicator, but here we have basically two different cases. What has been observed and what is simulated. And of course it's different. It's different because we know that we cannot predict climate. We can just, what we can do, we can basically simulate something which we think belongs to the same distribution of climate. basically one realization. So this is our distribution of the models, and this is one realization of the nature. And the two are quite similar, probably not exactly similar. We can see here. Here we have a problem. This problem related to meridional Vertane circulation, the effect, and so. But in general, for example, this is our Arctic amplification. We can see this very well. So we can be quite happy, not totally happy, but we can say, we can trust maybe the model, as Annalisa said. And well, this is something that I'm going to skip because I don't have much time. But I wanted, so said that, okay, we can see, okay, let's go and see the prediction with the scenarios that Annalisa has shown. And we have the 5 scenarios, and these are the prediction with the variability. One thing that is important here is that actually we are here, here. So the difference between the different scenarios are not evident, and they start to become evident. We can see the effect of what we are put or not in the atmosphere only around this 2050, middle of the century. And this is, of course, it's a bit of a problem because actually for the society, for kind of convince the different policy to do something would be very important to see the effect of something that has been done with respect to something that has not been done. So to see the effect, for example, of the current policies that are not enough, but something is being done but we won't see. The same in terms now of degree of global warming. Before we saw the different scenarios, no, and the fact that following different scenarios, there are different projections. What we know now is that actually at 1.5 or 2 degrees or 4 degrees is not important if you arrive at that temperature in 40 years following given scenarios or in 15 years following another scenario, because there is a pattern similarity. So we can put together all the scenarios and see what happens at 1.5, 2 degrees and 4 degrees. And this is the world that the model shows us. And there are differences of temperature, so anomalies of temperature with respect to the period 1850-90. And we are almost here. Now we are 1.115 to, well, it depends. It's this, but we will be there probably by 2030 or around 2030. So in let's say 10 years from now. And it is already something. It is already something. But it is we should stay below 2 degrees. Over 2 degrees, it's a world that it's really not habitable for at least not in the same way. Everything will, and if you look here, the difference in temperature are more than 7 degrees. So it is totally an error. And temperature is more reliable. We have seen that precipitation is not so reliable, but we can have a kind of, let's say, confidence when all the models that do different things do the same things, because it seems then that the effect on precipitation is actually related to large-scale thermodynamics. And when there is a signal on large scale and all the models follow that signal, we should be worried. Maybe all the models are wrong, but it's because they are very different, and because they are very different, do different things in other area, when they do the same, or they are totally wrong and we are basically, but well, probability maybe is very low, or we should worry. And well, one area where there are this signal, which is very strong in terms of lack of precipitation, especially, I don't have the figure here, but especially in the summer, is the Mediterranean. So there is this strong signal already at 1.5 degrees, because here in the Mediterranean. And of course, there is this band on the Atlantic, but actually we are interested also in the precipitation, not on land, but we live on land, so we are very interested on land. And this is where we live and where a lot of people live. And the signal of the Mediterranean is really worrying, because it seems something that is not possible, is not possible to stop. But even at 2 degrees, there is still something, and it is quite improbable to stay much below 2 degrees. So it's something that should be really think in terms of infrastructure, in terms of how to change agriculture, how to adapt. And it is not, the adaptation is not either adaptation or mitigation, but we have to go in both directions at the same time, because there are short terms and long term. And if there are things that we cannot change because it already happened. So this is very, very, very important. Another thing that we know is, and then I will stop, is just about what we have been observed in terms of extremes. And these are hot extremes. And this is, I found this very, very, the people working on that, well, they did an incredible job, because it's really striking. Because here we have two kinds of signal: the increase of hot extremes, and there is the attribution. So basically, they were able to attribute the human influence, and basically where there is the color, the orange, these are hot extremes, and the confidence in human attribution can be high, medium, or low, according to the number of dots. And you can see that actually all the continent, excluding this part, the western part, where there are a lot of different influence also related to the Atlantic climate, but actually in most of the land we can see that the hot extreme are increased, and the attribution is to actually the human contribution. For the heavy precipitation, these are another kind of extreme, you can see that it's totally different. So there is a lot of uncertainty. The uncertainty is related to the model, of course, but also to observation, because we don't have incredible amount of observation on precipitation. Not the same, of course, a lot in the northern hemisphere, but in the southern hemisphere, the observations are really, really not so well frequent, and not in many places. But still, there are in the northern Europe, and especially here, there is already this signal. Now, said that, what about the future? And this is, I think, the last slide that I'm going to show. And this is about the hot extremes in the future. So basically, has been computed, hot extremes have been computed, something that it's given magnitude that happen everywhere in the world. So this is a global picture, once in 10 years. Now, at present, that event that used to happen once in 10 years happened 3 times in 10 years, and the magnitude is 1.2 degrees hotter than in the past. If we go to 1.5, there is an increase. If you go to 4 degrees, it's not anymore an extreme, basically. So that was an extreme. It is it is more extreme in terms of magnitude, and it's basically much more frequent. For the same, but computed for a 50-year event, you can see the same, even more striking, because this is an extreme, much more extreme with respect to the past. And these are the projections for the future. So the same heavy precipitation. Heavy precipitation, we don't have enough data because precipitation is very noisy. It's a very difficult field. I don't like precipitation. It's really something that is very difficult to work with because the amount of uncertainty is tremendous, but we can see something also in precipitation. So, well, this Annalisa has already, I think that I can stop here. And okay, thank you. And well, we can.
Stuff. As you were saying, selection of times really when we have to see the climate change. We ensure the curve can change from 90s to 80s and then afterward. So my question is, that period the technology was so advanced, know the details of the data. So how cautious one should be compare that or data with what we have today currently?
Well, in general, I think that I should. We have put a band of uncertainty, which is larger for data coming from far in the past, and especially with proxies data, so data that are not direct measures, but also for the measures, so for data coming from measure from thermometers and so on. So there is a whole science which is devoted to the calibration, to measure compared to the measure depth. But in temperature we can do, and also, for example, just to take into account the heat islands related to, for example, to the cities and places that now are cities, but in the past were not cities. And so this is took into account. But also there are different sources of this data. So these data are kind of handled in different ways and by different groups in the world. So basically, we know we have different voices about that. And one thing more that is, I think, is important, and we didn't talk about, is that now the importance of data that are not really data or not direct observation, or they are called reanalysis. What are the reanalysis? And basically, they come from the concept of finding the best initial condition for weather prediction. So basically, when you have a model for the weather predictions, it's in general in the past, but also now, it's taking into account only of the atmosphere, because the other subsystems are so slow that basically they are treated as boundary condition in general. Now there are coupled oceans taken in consideration, but in general, let's say, let's fix on the atmosphere. So basically, we need to initialize this model. And to initialize this model, we should use the observation we have. But the observation we have, they are sparse, not at the same time, and so on. So they should be kind of re-modulated, and the model are used actually to do this kind of job. And there are different techniques to produce initial conditions, and the technique are kind of like I'm not, so this is another huge branch of the science. But basically, there are techniques that are based on Kalman filters, techniques that are variational technique on a given time space. And in this way, we do this kind of with the use with the help of the model. Nowadays, actually, this technique is also used to produce basically, instead of simply produce the initial condition for the weather, just to go back in time with the same kind of models and basically assimilating observation of the past and producing the reanalysis of fields that are equally spaced in space, in time. So basically, they are observation eaten by the models, and and actually, in the last IPCC report, this kind of data were used a lot. Where basically they were used together with their observation, but just to see also how the model were able to handle this kind of observation. So to make sure these things are taken into account, but of course there are uncertainties, and in general the uncertainties are shown as error bars or bands or so.
So my question is, since Stefano already asked what we can do from the technical point of view, I mean, what I wonder is what we can do from the political point of view. I mean, so there was recently a review that for sure you know, in which the estimation of the papers in climatology that denied anthropogenic origins of climate change were 1 per 1,000. So, and still the media say, okay, no, we need to have 1 and 1, which doesn't make it likely. Anytime we interview a biologist, you're forced to interview someone who doesn't believe in Darwinian evolution. Okay, it's exactly the same with worse consequences, and because it affects us even more. So, and the point is, I feel I'm really grateful for you for coming here and for the work you're doing, because I feel that right now the weight of this cultural battle is largely on the shoulders of climatologists. So, as a non-climatologist, what we can do to support this, because it's a matter of, basically, as I said at the beginning, it's like, if you say that anything seems to have uncertainty, nothing is valid, I mean, you're really hitting science at its roots. Okay, so I feel like we should be involved as well. What we can do.
I think that what we can do is actually try in explaining this, also the basic fact of science, to find a common ground with people. And this is very, very difficult, because we as scientists, as students in science, and so actually I don't think that we lost contact with the average background of the persons. And of course, it's the lay man or woman that can actually make a bit of pressure on the politics and so and so. And I think that is very difficult. For example, for me, just try to explain that what is a projection. So what you should expect and what you should not expect. It's very, very difficult, because we see that we have to go back in terms of what is common, the common ground, because then we can build information. Say, okay, we are going to do that, and then after that is that, and so and so. And this is very difficult. And but we have to. Well, I think that one has not to surrender. But the point is that, and the point actually, when I remember the title, I will send to you the title of the book, because it is an incredible book by an American journalist that I read many years ago. And this is about this idea of one says something, and you should someone else say the other thing, the opposite thing, and this is like to give equal opportunities to everyone, which is a concept that came actually from a right concept in the 60s in a way. That was the idea that were communities, there were people that without voice. And of course, because the debate was totally dominated by a majority or by like the power that was. But when and this in a way quite funnily, but not so funny. It was basically a concept that was taken by let's say the right. I would say, well, some conservative or but just to use it against, in particular, science, and really against science. And the two in US, the two fields of science that were actually fought in this way were Darwin, so the evolution, and the climate change. And I think that one has to explain with a lot of patience and don't join. I don't know. But no, we have with Annalisa a couple of days ago we heard about these comments about the floods, not the floods in Emilia Romagna, climate, and well, that was Franco Prodi, that was the director of our institute many years ago. And this debate at the TV that was totally nonsense, because basically you should be able to say, okay, you say something and you don't agree with climate change, but you should explain why. No, you should say, give me your opinion. It's not an opinion. You don't ask an opinion to astrophysicists or to physical matter about, just, so this is the same thing. It's not an opinion. So if you have evidence of something different, please give us the evidence. And this is the point of the evidence, that I don't understand why we are at this point.
Well, tell me about surrendering. Another very good, nice book about the climate crisis that I've read was that it's too late to be pessimist, which I like it a lot. It's the approach to that.
Now, another of the main message that the last IPCC wanted to convey to the community was a message of, okay, we know we are at this level, but we should not take these kind of thresholds, 1.5, 2 degrees, as a rigid threshold, and we just surpass this threshold, well, the world is going to finish. No, because then a world at 2.2 is better than a world at 2.5. 2.5 is much better than a world at 4 degrees more. And this is why one needs to continue, and to try to address policies in this way. There is no rigid threshold. We don't know if there is, maybe tomorrow there will be, but actually you should really accept this concept, because otherwise, the people say, now.
Yeah, this switch from it doesn't exist to we cannot do anything about it.
Yeah.
Like, all of us overnight. I don't question. I have two completely unrelated questions. Okay, I start with the first. So they're asking if you can go closer to the meet. What's this one?
No, it's
okay. Maybe
So about the perception of the problem, because so if we talk with the science people are using science arguments, maybe it's easier than talking with random people in the street. And so in that case, science as like a synonym is making some prediction. So the aim is to have a theory, but then use the theory to make some prediction. And I think that for be more close to the random people in the street is to give an actual, let's say, scenario, not in 100 years or 10 years, but like this week or the other week. This case is like the weather predictions, right? And even the weather predictions are not so, let's say, reliable, because with the many apps that we have, even you cannot deal with a real expectation. You have to see, like from the window, if it is true or not what you are looking from the screen. And so I think that to be very close and maybe change the general opinion is to give a real, let's say, a testable or a real prediction in a very short term. The other question that is related, say, is about a plot that you have seen, or even in the talk before, is about the trend in the 2000 year, from the, let's say, the zero, I don't know what is exactly the zero, and then these days. And the trend without the Industrial Revolution, for me, it was like, let's say, a global cooling, then a global warming. I don't know if it is like my view or can comment.
For the first question, yes, but even with the weather, well, the point is that the point is that first prediction of weather and projection of climate are two different problems, and we know that there is a horizon of prediction for weather because basically the system is chaotic, is in general chaotic, and we cannot go beyond a given horizon in time. However, and this is something that we don't speak about enough, the weather prediction has improved a lot with respect to 30 years ago, 20 years ago. So basically now we have gained a couple of days or even 3 days. And this is actually because of the huge progress in the models and the high augmented resolution and so on. But they are different problems. What this has been done, and we can find it on internet, is the projection done in the past. How far are to what we are seeing now? And the idea is they are quite similar. The problem is the projection. The projection, they follow a given scenario. If the scenario has been different, you cannot really compare projection of the past with what happened. So this is not easy. What should be noted is that climate has already changed. And this is something, and we know a possible cause, but the climate has already changed. And in particular in Italy, the changes is not 1 degree, but is about 2 degrees with respect to the pre-industrial. But if we look at the 60s and now, there is already, for example, in the Po Valley, during the summer, a huge change, and can be, it's something that can be seen. But the point is that until I don't know if someone of you have seen the documentary by Al Gore, The Inconvenient Truth, and the story of the frog. The frog in the boiling water. If we have a change that actually happens slowly, we have such a ability of adaptation that actually, basically, it's a great thing for us, but not not very good in a general sense, because basically we don't perceive the changes if they happen step by step. And well, I had a discussion with a guy in a popular, I don't remember if it was not the ricercatori or something, because he was saying, but I don't remember that the summer was different. And he was 80 or so. And I said, look, I'm younger than you, and I remember. But if you can go and see the.
But I never reached to the house. So glaciers are on the side. You go in the map, you say, okay, keep the finger to see the lake. And there's no lake. It really happened to me. So it's like. I mean,
Yeah, but you can close your eyes. And about the cooling, it's, in principle, we are going towards a cooling because in general, the planet should go towards the next ice age. But the time scale is so different, totally different, that we cannot say anything. It's, we cannot compare a time scale of 100 years with a time scale of 1,000 of years. So we know that there was this oscillation of related to the optimal middle age period. We know that there was a little ice age. This is very well documented, but there are all oscillations much longer. So, well.
Yeah, so mine is more a comment question actually, and well, I think people for some reason don't trust so much climatologists for some reason. They trust scientists for their cars, their smartphones. They trust engineers more than scientists. Well, that's true. That's true. But I think that that's why it might be important that all the scientific community speaks up and, yes, as you would say, and support the work you do and communicate the work you do, because then also for the men and women, they will see that the whole scientific community is supported. And in my opinion, there was maybe a lot of support from people like us who is focused on what they're doing and not really seeing that this is going to be the huge thing of our days. And I'm saying this community because we do develop technology meant for health and well-being, and this thing is going to hit the well-being of the world population a lot. So, but I think we should all try to give our contribution in a way. And so my question then is, are we entitled to do that? So would you approve of scientists to support it?
Let's say we have the open days. If in the next open days we have, I mean, we don't do it on climate change, anyway, it would be like a fake advertisement. But if we had one poster about climate change in the open day of the BioRobotics Institute, would that be?
No, I think it would be very important. And I would say that also is something that this kind of science is really very connected with technology. Because as I said, without the computer, but it's not only the computer, the iron, the chips, but it's also all the software and also the new ideas around the architecture, the way of using the computer. It's really it's becoming even more these days with the project like the Destination Earth, digital twins everywhere, very technological aspect. It's not one thing is only about observation, going on the sea and looking with the bucket. No, of course there are all these aspects, but there is also very technological. It's not so technological. It's not probably comparable with what you do, but I'm not sure, because actually there are problems that are still, they need an expertise, an engineer expertise and a physicist expertise that at the moment it lacks. And one of there will be a big workshop in close workshop in Berlin in July that is actually about this point. And the main point is actually to convince kind of European countries, and not only you, but more in general, to build a CERN for climate. Basically, a big laboratory with all the efforts will be kind of put together, and with the possibility actually to do something that now the single country, the single lab, even if it is the Max Planck, even if it is, are not able to do. Because as you know, what is done has been at the CERN is something that can be done only at that level. And they say that for climate, for progress, and to give better information that are also related to the impacts, to have, we need something like that. We need really an effort, the same money that these states put in this other kind of science. Because one thing that should be known is that the money that went here in the climate and so are really nothing, really. In Bologna we say bruscolini, so really peanuts, nothing. really peanuts compared to the money that goes. And this is something that it of course is important, because if we are able to do something like the resolution that 1 kilometer, and with other technologies, and so probably we can give a better information also for precipitation. Precipitation is extraordinarily important for the world. But I think that well, I don't know. It's something that, well, people is fighting for it since 20 years and so. But there is kind of a war that basically the economies of the big countries, they don't want to put too much money on that. And this is not understandable, but it is like that.
Are they all in denial?
No, it's not. There are, well, you know, it's not because of denialism. It's also because of even country. They want to have their own little kind of territory, and if they put everything together, well, there is a losing power. And I think that the big effort of the CERN was done because of the Cold War. Otherwise, we won't have the CERN in Europe for sure. And that was because there is this kind of possible danger, and then the CERN is there, and for continuity, they put money on that. But for example, at the end of the Cold War, it is the equivalent of the CERN in the United States was cut of funding territory. Yeah, and actually what they did, they should have built the equivalent of the Seacort, the same kind of size of in the United States, and it didn't happen. And it's because the Cold War was finished, and there was not this kind of pushing. And here there is an warm war. If you like. No, yeah, but it's terrible because I don't think that we will solve the problem. We won't solve the problem, but at least we should start to tackle the problem with all the means that we have as a community of scientists. That there will be much more scientists even coming from engineering, physics, and so working on this kind of problems and not on other problems. Yeah.
Okay, then it's time to, yeah.